NASA is currently exploring the potential uses of expert system technology for Space Station Freedom. 2 prototypes have been integrated, demonstrating expert system capabilities for the control, monitor, and fault management functions of Freedom. These 2 prototypes, the Procedures Interpreter, or PI, and the Integrated Status Assessment, or ISA, will be shown functioning in this role. The PI prototype implements the functions of commanding the space station, monitoring operations, and enforcing general and context-sensitive flight rules. The crew procedures are supplied to the procedure execution engine as data. Included in the procedure data are the commands that are to be issued, operating constraints, and rules that apply for the duration of the nominally performed operation. The ISA prototype performs fault detection, isolation, and reconfiguration. It was designed as a hybrid expert system using different methodologies. Object-oriented programming was used to describe the different parts of Space Station Freedom. Rule-based reasoning was used to encode the knowledge on how to perform the failure diagnosis, and qualitative modeling was used to describe the state of the various components. The video you are about to see shows the PI and ISA working with the Guidance, Navigation, and Control Emulation Testbed over a local area network in the execution of a space station reboost procedure.
We've come a long way with our space program, and many innovations have evolved in the process.
Godspeed, John Glenn. 3.
Roger, 0G, and I feel fine. Capsule is turning around. Oh, that view is tremendous.
The space pioneers of the Mercury program have given way to spacewalkers, moonwalkers, the multi-role crews of the space shuttle, and now the full-time workers who inhabit the Space Station Freedom. The men and women on Freedom fill a much different role than the astronauts of the shuttle program. On the space shuttle, the astronauts' primary concern was to keep the orbiter and its complex support systems operating properly. But on Freedom, it is a new era. It's the era of OMS, the Operations Management System. This sophisticated automated manager assumes the everyday duties and frees the crew to pursue their individual specialties. In essence, the Flight OMS is a computer program that assists the station commander. Together, they orchestrate and oversee the functions of the autonomous lower echelon systems that operate the station. Through the data management system, the Flight OMS is linked to the Guidance, Navigation, and Control System, the Thermal Control Systems, Communications and Tracking, and the Power Management and Distribution System. The Flight OMS is located on the space station, but there's also a redundant ground-based OMS. The ground-based OMS is not only used to uplink changes to procedures and other data, but can also step in and assume the primary OMS role should the onboard system malfunction. Do you feel that machines are taking over completely? Well, you can breathe a sigh of relief, because as automated as OMS is, it still requires a human touch. Here's how it works. According to an established procedure, the station commander consults OMS to review a variety of plans that are stored electronically by the system. One plan in particular is the short-term plan. The short-term plan is similar to the old flight data file document used on the shuttle. It is a timeline that outlines when certain activities are to take place. To access this information, the commander goes to the console terminal and logs in.
Once I've logged in, I move the cursor to a trackball sensitive area of the screen and select the word Planning. This gives me a menu of several planning activities. I'm interested in the short-term plan, so I'll select that entry and the short-term plan appears. By reviewing the short-term plan, I see there is an important task for today. The station must be reboosted into a higher orbit. There is a certain procedure I must follow to accomplish this maneuver. By selecting the task Reboost, I get a new window that lists several options. I want to do an integrated reboost, so I'll select that line. OMS responds by giving me the step-by-step procedure for an integrated reboost.
In a maneuver like an integrated reboost, OMS can display its impressive systems management capabilities. Before continuing the reboost, let's take a moment to consider everything that must take place. The primary system involved in reboost is the Guidance, Navigation, and Control System, or GN&C. Once given the command to prepare for reboost, OMS will instruct GN&C to reconfigure for the maneuver and report back when ready. Since GN&C is an autonomous system, it will reconfigure with no further communication with OMS until it's time to report its status. Meanwhile, OMS must coordinate other preparations. In order to endure the disturbances encountered during the reboost, solar panels must be repositioned, antennas stowed, and camera lenses covered. Payload operations may be advised to shut down during the maneuver, and the station's other systems must be reminded that a scheduled reboost is about to begin. A system like power management and distribution may report back that there's a conflicting power requirement in progress. In that case, OMS will decide which activity must slide to another time slot. Now let's rejoin the commander as he continues with the reboost procedure.
After selecting the integrated reboost, OMS gives me several options of how to perform the maneuver. It can be performed by automatic cyclic targeting, where OMS will go through the procedure from the beginning and stop only at those steps where I must make a decision. Or I can perform the maneuver by stepwise cyclic targeting, where OMS presents each step to me and proceeds only after I've initiated that step. There is also another choice, delta V targeting, but today I'm going to do the procedure step by step. By selecting the stepwise procedure, the system automatically scrolls the screen to the appropriate point in the procedure. The first step tells me to specify target altitude and start time. By clicking on this step, a new window appears, containing default values for both altitude and time. At this point, I can either change the values or accept them by default. Since I want the station to go from its current altitude of 230 nautical miles to the desired altitude of 250 nautical miles, I'll default to the preset values.
To the immediate right of the procedures is the beginning of a list. This list is added to as each step of the procedure is performed. It consists of a timestamp and a confirmation of each step. When completed, the list is stored electronically in the data bank and can be retrieved as needed. Once a step has been completed, a small check mark appears next to it on the procedure. The commander now tells the OMS to compute the first pass target information. OMS reacts immediately and reports that the action is completed. The commander can now initiate the countdown. The countdown can be monitored on the countdown clock in the lower right-hand portion of the screen. During the countdown, OMS prepares the station for reboost by coordinating those events that we discussed earlier. Each phase of the reboost is reported in a window at the lower left-hand portion of the screen. While the station is being prepared, OMS continues with other steps. Should the commander want to tailor a new command attitude, the new values can be entered, and the OMS will feed this information to GN&C, which will then drive the station to the new attitude. Simultaneously, the commander can select a window that shows attitude data and watch the station move to the new position. This data updates every 2 seconds. Once all systems report back to OMS, the actual reboost begins. The actual reboost consists of a sequence called burn, coast, burn, which takes approximately 1 hour and 35 minutes to complete. The first burn is actually a series of short jet firings, or burns, for about 1 hour. The station then coasts for about 20 minutes, and then the jets burn again for approximately 15 minutes. Each sequence is called a milestone and is displayed as it occurs in the phase of procedure window. OMS also allows the commander to view the reboost on a graph that is plotted during the maneuver. The plot data is updated every 5 seconds, and a new plot point is added to the display every 30 seconds. Once the maneuver is complete, the OMS reports that the burn attitude has been achieved and the reboost is complete. The execution of this complex and integrated maneuver alone says much for the OMS, but there's still a lot more than it can do. The commander is simulating a malfunction in the reboost procedure so we can demonstrate some of OMS's other capabilities. While any system function is underway, the commander can access an integrated status assessment program and look at the schematic of that particular system as it performs. This schematic of the GNC reaction control system shows the double redundancy of each jet. If the primary jet were to malfunction, as simulated here, the backup jet would immediately step in and continue the procedure. OMS would document the malfunction electronically and also inform the commander that a jet had malfunctioned and that maintenance is needed. If the commander so chooses, the maneuver can be manually aborted at that time. Now let's consider a situation where the backup jet also fails. In this case, OMS will advise the commander that it will abort the maneuver unless the crew intervenes. This situation not only demonstrates a lower echelon system's redundancy taking care of a problem, but it also demonstrates OMS's ability to manage suboptimal happenings as well. OMS is a great asset to Space Station Freedom. It not only manages the day-to-day routine tasks of running the space station, but also does away with the reams of hard documents that astronauts once had to rely on. With OMS on the bridge, Freedom is in good hands, and our specialists on board are free to accomplish great things for all of us.